Hi everyone. Today's video is going to focus on the applications of differential equations. So really the idea here today is to give you a look at all the different types of questions you could be asked about either slope fields or differential equations. So I will give you a heads up, this is going to be a long video. You might want to think about how you can kind of chunk it up. But like I said, we're just going through lots of questions related to differential equations and slope fields so you can get an idea of what might show up particularly when it comes to the free response question section. So here we go. The first one, it says to consider the differential equation dy dx equals the opposite of x times y squared over 2. It says y equals f of x is the particular solution to this differential equation, and it's giving me an initial condition of f of -1 equals 2. So the first thing I'm being asked to do is to sketch a slope field on the axes provided. So the first thing I always look and see is if there's some easy points to knock out. And so what I notice is that when either x or y is 0, the slope of my function is going to be 0. So I'm going to mark that first. So wherever y is 0, I know I have a slope of 0. And wherever x is 0, I also have a slope of 0. So now it just leaves me with 6 points to kind of go ahead and figure out. So I'm going to look at 1, 1 first. So I have the opposite of 1, so -1 times 1 squared. So my numerator is -1. My denominator is 2, so I have a slope of -1/2. If I take the point 1, 2, I again have the opposite of 1, so -1 times 2 squared. So -4 divided by 2 gives me a slope of -2. Now I'm going to do the point 2, 1, so -2 times 1 squared, so -2 divided by 2 is a slope of -1. And then at the point 2, comma 2, I have -2 times 2 squared, so -8 divided by 2 gives me a slope of -4. Now if I jump over here, let's see, I have -1, so the opposite of -1 now gives me a +1. Times y squared is 1, so +1 divided by 2 is a slope of 1/2. And then -1, 2, opposite of -1 again is a +1 times 2 squared, so I have a +4 divided by 2, gives me a slope of +2. And there's my slope field. So now for part B, it's asking me to write an equation for the tangent to the graph of f at x equals 1, or excuse me, at -1. So now it wants to know for the original function, what would be the equation of the tangent line at x equals -1? And we'll get to the second part of this in a minute. So when I see tangent, I know I need two things. I'm going to need a point, and I'm going to need a slope, right? The slope of that tangent line. So the first thing is the point. They're telling me to find it at x equals -1. So I know my x-coordinate's -1. Now, to get that y-coordinate, I need to know, I have to go back to this initial condition, right? That's telling me that the point -1, 2 is a point on that original function. So now for my tangent line, I have the point -1, 2. To find my slope, well, I know the derivative, my dy dx, is the slope of that tangent. So I'm going to take that, and I'm going to evaluate it at the point -1, 2. So now I've got the opposite of -1 times 2 squared all over 2. I'm going to have a +1 times 4 is 4 divided by 2, and that's equal to 2. Now I can do a quick check to make sure I haven't made any errors on my slope field, right? My slope's a +2, and if I look at -1, 2, that matches with my positive slope here. So now that I've got my point and my slope, I can write my tangent line. So I have y minus 2 equals 2 times x plus 1. And that's the equation of my tangent line. Now, the second part is they want us to use our tangent line to approximate f of negative 1.2. So this is where we need to think back to when we did our linear approximations, right? We used this tangent line to approximate the value on the actual curve. So if you remember that, we called that L of x, and we just isolated y here. We said that was equal to 2 plus 2 times x plus 1. So if I want to find f of negative 1.2, I know that's approximately L of 1.2. Remember that linearization is just based on the tangent line. So that's equal to 2 plus 2 times negative 1.2 plus 1, which gives me 2 plus 2 times, that's going to be a negative 0.2. which is 2 minus 0.4, or 1.6. So I know f of negative 1.2 is approximately 1.6. All right, for part C, it asks me to describe all locations in the xy plane for which the slope of y equals f of x, so again, for which the slope of my original is positive. So I'm going to look at this two ways. The first thing I always like to do is go back to my slope field. And I notice that the slope is only positive when x is less than 0. Now, since I could have made an error in my slope field, I'm also going to go back to my differential equation. Now, if I want my slope to be positive, y is squared, so no matter what the value of y is, I know that's going to be positive. So the only way for my numerator to be positive is if my x is negative, because then I'll have a negative times negative will make that positive. So that matches up with what I'm seeing in my slope field here. So to answer this question, I would say the slope of y equals f of x is positive for all points x and y such that x is less than 0. Now, I do have to be a little careful. So x is less than 0. I notice here, even though x is less than 0, I have a slope where the slope is equal to 0. So I have to exclude, this is not going to be positive if y, let me look up here. If y is equal to 0, I'm going to have a slope of 0. So I have to go ahead and exclude y being 0. So it's positive for all xy such that x is less than 0 and y is not equal to 0. Then I know I'll have a positive slope. All right, moving on here. My next question, now it's going to ask me to find that particular solution, right? So I need to solve my differential equation so I can find that original equation. So I'm going to rewrite my differential equation. We had dy dx equals opposite of x times y squared over 2. So I know to solve this differential equation, the first thing I need to do is separate my variables. So I'm going to have dy over y squared is equal to negative x over 2 times dx. So now my y's, my dy's are on one side, my x's and dx are on the other. So I'm going to integrate that and use my antiderivatives. So this is really y to the negative 2. So I know my antiderivative is going to be negative 1 over y. On this side, I had negative x over 2, so now I'm going to have negative, let's see, this is going to be x squared. And I have to divide by 2 since there's already 2 there. I'm going to have negative x squared over 4, and then I need my plus c. Now I'm going to use my initial condition here to solve for c. So what I have, my y is 2, so I have negative 1/2 equals, f is negative 1, so I have negative 1 squared is a positive 1, but now I have this opposite, so negative 1/4 plus c. So if I add a fourth to both sides, I'm going to get c is equal to negative 1/4. All right, so now I'm going to plug in my c. I have the opposite of 1 over y equals negative x squared over 4 minus 1/4. Now my job is just to isolate y. First thing I'm going to do is multiply by negative 1. So I get 1 over y equals x squared over 4 plus 1/4. Since those have common denominators, I'm just going to write it as a single fraction. So x squared plus 1 over 4. Now to isolate y, I just need to take the reciprocals. So I get y equals 4 over x squared plus 1 for my particular solution. Again, what we did there is we found the original equation that had the given derivative here and goes through this point. So what I always like to do is just plug this point into my original and make sure that makes sense to catch any potential errors. So if I plug in a negative 1 for x, I'm going to get the opposite of 1 squared, which is just 1. 1 plus 1 is 2. 4 divided by 2 is 2. And I do get that y value. So it seems reasonable that I've done the correct work here. All right, last problem, or last part for this problem, I should say. Now they want us to find the second derivative. Right, so we're going to take our differential equation, dy dx equals the opposite of x times y squared over 2, and we're going to find that second derivative. Now the thing I want us to be careful about, we're going to have to remember that here we're going to have to use implicit differentiation. Because remember, we had to use that whenever our function was in terms of x and y. So this might be a good review for us. All right, so I'm going to take the derivative of the derivative, essentially. So here we go. So now I have my quotient rule here. So I have, actually, let's do this. I'm going to think of this as negative 1/2 times xy squared. Because I actually prefer to do product rule. If you prefer quotient rule, you could certainly do it that way as well. So now I know a constant times a function, its derivative is just a constant times the derivative. So I'm going to pull this negative 1/2 out, and now I'm going to go ahead and do product rule. So I'm going to have the first times the derivative of my second factor, so times 2y, but then I have to remember this is implicit, so I need a dy dx. And then I'm going to do plus y squared. The derivative of x is just 1, and I've got my derivative. Now there's a few manipulations I need to do. First thing, I'm going to leave most of this. I've got 2xy, but instead of leaving dy dx, I need to go plug in dy dx, because I know what that is. So I'm going to do times opposite of x times y squared over 2. And then plus y squared. And now I can do some simplifying here. On this side, these are going to cancel out, so I have negative 1/2 times, I have opposite of x squared, y cubed, plus y squared. So I'm going to get 1/2 x squared, y cubed, minus 1/2 y squared. And that's my second derivative. Oh, I'm sorry, I ran off the page there. All right, so that's the first problem in this video. So it may be good to kind of take a break here and then come back to the rest in a little bit. But we're going to move on, and we're going to look at a problem involving a differential equation. Okay, so here we go. All right, so now it tells us the rate at which a baby bird gains weight is proportional to the difference between its adult weight and its current weight. So at time t equals 0, when the bird is first weighed, its weight is 20 grams. So what I'm picking up here, at time t equals 0, when the bird is first weighed, its weight is 20 grams. I'm picking up an initial condition of 0, 20. Okay, now if B of t is the weight of the bird in grams at time t days after its first weight, then dB dt equals 1/5 times 100 minus B. So they're giving us the rate of change of the weight of that bird, right? Hopefully we all recognize this now as a differential equation. It's not dy dx, but it's that derivative, so that's still a differential equation. So it's saying let y equals b of t be the solution to the differential equation above, and again, there's that initial condition, b of 0 equals 20. All right, so now part A is asking, is the bird gaining weight faster when it weighs 40 grams or when it weighs 70 grams? So it asks to explain your reasoning. Now, again, we said this is, if B of t is the weight of the bird, this is the rate at which that weight is changing. So we can use the derivative to ask or answer this question, right? We know this is B, the weight of the bird. So I want to know which has a greater rate of change, when B is 40 or B is 70. So I'm going to calculate dB dt when B is 40. So I know that's going to be 1/5 times 60, which is going to give me 12. And I'm going to do dB dt, I should have put this before, when B equals 70. 1/5 equals 100 minus 70 equals 30 divided by 5 equals 6. Now if we think in terms of units here, the weight was in grams, right, and our time was in days. So this is really telling me it's gaining weight at a rate of 12 grams per day when it weighs 40 grams. When it weighs 70 grams, it's gaining weight at a rate of 6 grams per day. So now it's easy to see that when it weighs 40 grams, it's gaining weight more quickly. So we can say the bird is gaining weight faster when it weighs 40 grams because, right, they're asking us to explain, so we don't want to miss the points for that. So because, and we can just say dB dt when B equals 40 is greater than dB dt at time, or excuse me, at weight B equals 70. That would be a sufficient explanation. So they're going to want to see your work. Did you know to plug in B into that differential equation? And then can you explain your answer? Okay, so the next part now, they want us to find that second derivative again. So we already had a little practice with that before. So now we're going to go ahead and do that. Again, we're going to have to use implicit differentiation. So I have a constant times a function. My derivative is going to be that same constant times the derivative of this function. Well, the derivative of 100 is 0. The derivative of the opposite of b is -1, but then I have to multiply times dB dt. So now I have -1/5 if I combine my constant terms, but now I'm going to substitute dB dt. So I have times 1/5 times 100 minus b. So my second derivative is -1/25 times 100 minus b. All right, so that part is good. Last, we're going to go back to this idea. We're going to use separation of variables to find y equals b of t, the particular solution to the differential equation with initial condition b of 0 equals 20. So now we're just back to solving our differential equation. So I'm going to, again, rewrite this here. db dt equals 1/5 times 100 minus b. So, as always, my first job is to separate my variables, get all my b's on one side and my t's on the other. So I'm going to have db over 100 minus b equals 1/5 dt. So there I've separated my variables. Now this step is extremely important to show. If you do not show this step, the AP grader essentially is going to give you 0 points because they say that you get 0 out of 6 points if you did not separate the variables. So you need to make sure you're showing this step if you want to earn any of the points. And this is typically a 6-point question and an FRQ. Okay, so now we're going to integrate. Now I have 100 minus b, so I'm going to have the natural log of 100 minus b, but now I have to be careful. Since in the chain rule, this would give me a -1, right? I have to make sure I divide by a -1 here as well. On this side, I have 1/5 t and then plus c. So now we're going to go ahead and solve for our value of c. So now I have the opposite of the natural log of, now remember, this is b of t, so this is my y value here, or my b value, right? So I have 100 minus 20, so this is 100 minus 20, equals 1/5 times my time is 0 plus c. So that clears out. Here I have the opposite of the natural log of 80. Okay, so now I'm going to go back here. The opposite of the natural log of the absolute value of 100 minus b equals 1/5 t minus the natural log of 80. And now I have to do all my work of isolating my variable. So I'm going to slide this up so you can see it here. First thing I'm going to do is divide by a -1. So I have the natural log of the absolute value of 100 minus b equals, now I'm going to have the natural log of 80 minus 1/5 t. I know to isolate my variable, I have to exponentiate both sides. Okay, sorry about that. So we're going to have e to the natural log of 100 minus b equals e to all of this. Now I can separate that up. So I'm going to have that's equal to e to the natural log of 80 over e to the 1/5 t, which is just going to give me 80 over e to the 1/5 t. So now on this side, I have the absolute value of 100 minus b equals 80 over, instead of doing the 1/5 t, I'm just going to make this e to the t over 5 to make it a little easier. Now I'm kind of running out of room, so I apologize. I'm going to go over here. Now to drop my absolute value, I need to make this a positive or negative. So I have 100 minus b equals positive or negative 80 over e to the t over 5. I'm going to subtract 100. And last, I'm going to divide by a -1. So I'm going to get b equals positive or negative 80 to the or over e to the t over 5 plus 100. So now the last thing I'm going to do is check my initial condition, determine whether this should be a positive or a negative. So if I plug in 0, I'm going to have e to the 0 over 5 is e to the 0, which is 1. So I'm going to have either a positive 80 plus 100 or a negative 80 plus 100. If I want my y value to be 20, this has to be a negative, because a negative 80 plus 100 is equal to 20. So after checking my initial condition, I know my function is negative 80 over e to the t over 5 plus 100. And I apologize that it's so crammed in there. So negative 80 over e to the t over 5 plus 100 is my particular solution to that differential equation. Now I know there's a lot in there, so that may well be one that we talk about when we're back together in class. All right, one more problem to go. Again, maybe a good breaking point if you've your brain is full for the moment. All right, here we are back with a differential equation and a slope field. So the first thing they're going to ask us to do is to sketch a slope field for the given differential equation. Okay, so we've got 9 points here. Now this isn't quite so easy as the first one, where I knew that x or y being 0 was going to make the slope 0. So I'm just going to do more of a point-by-point approach here. So let's look kind of just like I said, point by point. So if I do 1, 0, so I have 1/2 plus 0 minus 1. So 1/2 minus 1 is going to give me a negative 1/2. If my point is 1, 1, I have 1/2 plus 1 minus 1. So those 1's are going to cancel out, and I'm going to get a slope of 1/2. And now at the point 1, 2, I'm going to get 1/2 plus 2. So I'm just going to write this here. 1/2 times 1 plus 2 minus 1. So 2 minus 1 is 1, so I have 1/2 plus 1. That's going to give me a slope of 3/2, so a little bit steeper. Now, it may be worth it at this point. Instead of listening to me talk through this point by point, you could always pause it, do your own, and then just fast forward a bit to check that your answer matches mine. All right, at the point 0, 0 here, that makes it a little easy here. Both of these terms drop out, so I have a slope of negative 1. At my point 1, 1, or excuse me, 0, 1, I just have 0 plus 1 minus 1 is going to give me a slope of 0. And at 0, 2, I have 2 minus 1. It gives me a slope of 1. All right, negative 1, 0. I have negative 1/2 minus 1 is going to be a slope of negative 3/2. Hopefully I did that right. Negative 1, 1. Let's see. I get negative 1/2. My 1's cancel here, so that's a slope of negative 1/2. And at negative 1, 2, let's see, I have negative 1/2 plus 2 minus 1. So negative 1/2 plus 1 is a slope of 1/2. And there's my slope field. All right, the next part of my problem asks me to find the second derivative in terms of x and y. So I'm going to go ahead and do that. Now this is a pretty easy one if I'm finding the derivative with respect to x. My first term is just 1/2. My second term, the derivative is 1, but I need to do plus dy dx because I'm using it in my implicit differentiation. And my third term, the derivative is equal to 0. So now I just have to substitute. I know dy dx is 1/2 x plus y minus 1. So I'm just going to simplify, combine my constant terms. So I get 1/2 x plus y minus 1/2. So that's my second derivative in terms of x and y. Now, it asks me to describe the region in the xy plane in which all solution curves to the differential equation are concave up. Now, here we have to think back to what we know about concavity. I know I'm concave up when my second derivative is greater than 0. So let's see what that means for us here. I know that my second derivative is equal to 1/2 x plus y minus 1/2. And I want to know where that's greater than 0. So what I'm going to do is I'm going to isolate y. I'm going to say y is greater than, if I move this over, I have a negative 1/2 x. And if I move this, I have plus 1/2. So what I essentially know is that all the solutions are going to be concave up when I'm above this line. All solution curves above this line will be concave up. So I'm going to say solution curves will be concave up above the line y equals negative 1/2 x plus 1/2, because I know above that is where my second derivative will be greater than 0. All right, last part here. It says let y equals f of x be a particular solution to the differential equation with the initial condition f of 0 equals 1, and it wants us to know if f has a relative minimum, a relative maximum, or neither at x equals 0. Now here's where we need to stop and think. We actually don't need to find that original solution. If you think back to when we worked with extreme values, we had a test, and we said we could determine whether a function had a relative minimum, max, or neither by looking at the first and second derivatives. So here's what I'm going to do. I'm going to take my first derivative, dy dx, and I'm going to evaluate it at the point 0, 1. So again, if I look back to the top here, if I plug in 0, I'm going to get 1/2 times 0 plus y is 1 minus 1, so that's equal to 0. So if my derivative is equal to 0, I know I have a horizontal tangent there. So it seems like I'll have some extreme value. Now I need to decide whether that's a maximum or minimum, and I'm going to do that by looking at the concavity. So I'm going to take my second derivative, and I'm going to evaluate that at the same point. Well, our second derivative we said was 1/2 times 0 plus my y value is 1 minus 1/2. So I get 1 minus 1/2, which is 1/2, which is greater than 0. So now I know I have a horizontal tangent at that point, and my function is concave up, which means at that point then I have a relative minimum. Again, because I have a horizontal tangent, my first derivative is 0, and because I'm concave up, that point is a minimum. So we're actually able to determine this without solving the differential equation. And usually the problems are kind of structured to guide you there because we had already calculated the second derivative. So we would say f has a relative minimum at x equals 0 because my first derivative at 0, 1 is equal to 0, and my second derivative at that point is greater than 0. Whoops, and I chopped off my writing. There you go. All right, so again, I obviously know this was a whole lot of information to take in, but again, we just kind of wanted to present you with all the different types of problems you might see, and as usual, you'll have a chance to kind of chew and work through some of these when we're back in class. So thanks for getting through this, and I will see you back in class.